Okay, let's start this lab. This lab, as you may read in the preface, deals with the fictitious company called Aircraft Engine. And this company's business problem is about finding any relationship between flight delays and issues with planes, engines, so to be able to improve ground services, improve maintenance services, or even improve the future, the design of the future engine. So in order to provide the data analysts team a meaningful information set, we will use an open data set as a raw layer of our warehouse, which is based on a set of CSV files representing both the fact of this star schema and the facts are represented by the flights CSV, as well as the dimension, the BI dimension of this dataset represented by the airline CSV, the airport CSV, and the planes CSV. So we will use this lab for two reasons. First of all, of course, appreciate the so-called data services of the CDP of the Cloudera data platform. So the self-service provisioning, the rapid time to provision those services, the architecture of the services, which are basically container native, the elasticity and the performance of these data services. But we will also appreciate in this lab some advanced capabilities of Iceberg as table format, because Iceberg enabled to bring back into the data lake some advanced features that usually were implemented only on analytical database or outside of the data lake, but also dramatically improve the performance of analytical complex ad hoc queries on very large table. And Iceberg enables such capabilities across many different engines. Okay, let's get started. And we suggest you to use Chrome in incognito mode to avoid any clash with previously defined cookies or configurations of a sort. And of course, you will need some information that will be provided you by your instructor, which you can see here. So first task we need to accomplish is to define our CDP workload password. The CDP workload password is basically the password of the CDP, the Cloudera data platform user. Let's log in into a Keycloak server that will be provided you for this lab in order to single sign-on into the CDP platform. And so this is my username, and here is my password. The password will be provided by you by the instructor. Okay, at first login, the system will ask you to update your password in order to make it confidential and known just by you. Then submit, and then you will be brought into the landing page of the CDP Cloudera data platform. So here you have an overview of all the main, most important data services that you can develop in the platform, but also on some administrative management services that will allow you to administrate the platform, the users, the configurations, the engines, the storage. And in this case, we will use one of these services to change our workload password. You may see that the user management system of the CDP can infer the workload username, so the Cloudera CDP username, out of your email. But of course, the workload password needs to be explicitly set. So this is exactly what we are going to do. We click on set password and we insert our password. We click set workload and then we should see this banner. Okay, let's come back to the GitHub repo to step 3. Now it's time to start implementing the so-called row layer. And to do that, we will use one of the Cloudera Data Platform services called CDW, Data Warehouse Service, and in particular a virtual warehouse, which is a container-based implementation of both Hive and Impala. We will use in this case Hive, the Hive version of the virtual warehouse, to create our two databases. The first one will be the database that will include the row tables, and the second database will include, at a later time, the curated table. So let's, I would say, copy these statements and come back to our platform. Let's click on this 9-dotted menu and select Data Warehouse from the list of available data services. We will be brought into this UI where you will see a couple of database catalogs. In our case, we have to select the database catalog provided by the instructor, and by selecting this database catalog we should see a number of so-called virtual warehouses highlighted on the right hand side of the UI. And let's scroll to the instance that has been assigned to you. This is an important part. Please be careful to select the instance, the Hive instance that has been assigned to you. So I will use this one, 1 to 10 Hive, and I will open the Hue editor, which is basically the standard SQL editor for CDP. And by pasting the statements that I copied from the GitHub repo, I should see popping up this box, or just insert it into, and of course run. Okay, it seems that database have been created. So let's come back to our lab guide and see whether everything is fine. Yeah, and those two are the database that we just created. So let's come back to the lab guide and jump into the next step. Okay, next step is to create the row tables inside the row database out of the CSV files that has been already ingested into the data lake, in this case into those S3 bucket. So let's copy those statements and come back to our Hue editor. And let's run it. Okay. Step by step, those tables have been created. And now let's move to the next step and to take a look at the tables we just created. So we will use the raw database and show tables. Okay, and here are the tables that we just created on top of the CSV files. So let's move on to the next step. The next step will be executed in a different virtual warehouse instance, in this case with the Impala version of the virtual warehouse. So to let you appreciate also the Impala implementation, Impala container native implementation, and we will use Impala to double check the number of rows that are present into the flights. You may remember the flights table is the fact table, is the largest one. And so let's just come back to our CDW UI, and in this case select an Impala virtual warehouse. Once again, please make sure that you are working in the instance that the instructor provided to you in order not to overlap with other attendees. And let's open the Hue of this Impala version. Okay, let's take our database, let's select our database, and then of course hostgf, this is my user. Let's start counting the records inside the flight table. So you can see we have more than 86 million of rows inside this table. That's fine. Okay, now that we have double checked the size, the length of our fact table, let's try to run a first analytical query. Here in the lab guide you can find a first one that basically joining the flights, the fact table, looking for the most delayed planes and using that information to match model and engine type of those plane mostly delayed. So let's come back to our Hue editor on Impala, paste our query and run it on the raw version of the table, just to establish a benchmark baseline performance measurement of this kind of let's say data intensive query. First rows have null value, and here are our data. And now switching back to our lab guide, next step is to take a look at the schema of this table. So we run this describe statement, and with that, of course, we can take a look over the schema of the columns, but most importantly, of course, the location. And again, is The location is the standard Hive location of meaning of the standard Hive database. It's on S3 bucket because, as you may remember, our data lake storage is based on S3 bucket. It's an external table. It's not yet an Iceberg table, but in terms of file format is already Parquet, as we specified in the create table statement. Now let's come back to our lab guide and create our second curated table, which is the airlines one. And here we change a little bit our strategy. First of all, we don't create an external table. We want a managed table because we imagine that this airline, despite being a dimension table, could be changed over time with update, with row level update, row level insert. And so we want a fully ACID table. We choose a binary columnar format in terms of file format. Still, yet this is not an Iceberg table. And the other strategy is to create table as select. So to create and fill out this table all at once. So let's copy this statement, jump back to our view editor on Hive virtual warehouse, run this statement. Okay, it is completed. And now let's take a look at the content of this table, and let's look for specific airlines code. Of course, the UA is a standard airline code, and so we found it. The other one are fictitious airline codes that are not yet present in the table. And because of the use case that I mentioned before, we are now simulating an insert, row level insert into this airline table, assuming that a new airline code gets created. Now we are inserting a single row, and so by restating the previous select, we, as expected, now we match 2 out of 3 airline codes. And for the third one to appear, we use this approach. We create kind of a temporary table called airlines dimension updates, and we insert 2 brand new records into this, let's say, temporary table, and then we merge those 2 records into our real world target dimension airlines table, and the result of this merge will be an update on the United Airlines record, updating the description of the airline, and in this case, so it will be a row level update. And instead, since this second airline code is brand new, so it's not present into our airline table, the merge will result into an insert. So let's copy the statement, paste into our U editor. From here we create and insert 2 records into our temporary one. Okay. Success. And then merge. Okay, and now you see the 3 records into our dimension table. Back to our lab guide to proceed with curated layer by showcasing another capability of CDW service with regards to Iceberg support, which is the in-place, so-called in-place migration feature. What does it mean? It means that you may remember we created an external table called planes, but in Hive table format. We have a chance to in-place transforming this Hive table into an Iceberg table without the need to rewrite the data inside the table. So that's why it's called an in-place migration. And so to do that, let's copy the statement, come back to our View editor, and basically this is nothing but altering table properties by specifying the Iceberg storage handler that the Hive engine will be using from that moment onwards. It seems like the table has been altered. Let's take a look at table new metadata. Of course, the schema, of course, the location, again an external table, but now some parameter has been changed. The first one is this label, which tell us that this table has been migrated to Iceberg in place, and now there is this metadata location, which is basically the path inside the data lake storage where Iceberg catalog stores its metadata. You may know that Iceberg architecture is slightly different from the Hive one in terms of metadata management. The metadata information are stored in the same file system of the actual data. And what is also interesting is to see that the CDP library has been changed into Iceberg format. And now it's time to create our last dimension table, which is airports in the curated layer. And we create this table using another approach, which is creating this table straight as an Iceberg table by using this statement stored by, and we create a select approach. Okay, that's completed. And once again, let's take a look over their metadata, and we will see that as for the previous table, is not, we don't find anymore the migrated to table information, because this table has not actually migrated from a different table format. But in terms of CDP, we find the same information as before. So, and this is all we need to double check that this is an iceberg table format. Okay, and now it's time to create our last table, probably the most important one, which is our fact table, the flights table, into our curated layer. And we will create an external table straight in Iceberg table format. In terms of file format, we will choose Parquet, and we will create an empty table because we will fill this fact table in batches, in incremental batches later on. So let's copy this DDL, come back to our view editor, again running on our Hive virtual warehouse. Let's review it a little bit. Another important point is that we will introduce the partitioning. This is going to be a very tall table, so we need ways to speed up the access, and we will start partitioning by ear. This partitioning strategy will also be useful to showcase later on the partition evolution capability of Iceberg, which is one of the most important features of Iceberg. So we will partition by ear. As of now, this table will be stored by Iceberg as a Parquet file format, and we will use Iceberg version 2 in terms of Iceberg specification. Let's run it. This statement will take a very short time because basically that's an empty table, so just metadata, and then we can take a look over the schema information. The partitioning is there. And here we can see that's an Iceberg table with Parquet file format. Now, next step is to fill up this table using a part of the raw flights table with the flights series up to year 2006. And we will do that to appreciate the partitioning evolution capability of Iceberg later on. We are talking about some million of rows being transferred from one table to the other, so this statement will take a while. And now the table has been filled out. Let's copy the next statement to take a look inside it, leveraging in this case the partition strategy that we implemented over table. We can see that each series is quite tall. We are talking about 7 million rows per year. And with that, we basically completed our so-called curated layer with flights and all the dimension table. Let's double check on the lab guide, and here is a recap diagram. We started from a raw layer with basically CSV files projected into external table in high format, and then we converted those into much more efficient Iceberg formatted table with serialized with binary file formats like Parquet and ORC, much more suited with our analytical needs. And we also partitioned the fact table by year. Now, another important goal of Iceberg project is geared at improving analytical query performance, and so we now have a chance to appreciate this aspect of Iceberg by coming back to our Impala hue editor. You may remember in the previous step we ran an analytical query against a raw flights table, the raw version. So we have now a chance to rerun the same query but on the Iceberg formatted table, airlines and flights, and see that now this query completes in a much shorter execution time. Let's now move on and showcase another important feature of Iceberg, which is the so-called partition evolution in place. So Iceberg gives us the ability to evolve, to change the partition strategy in place without rewriting the whole table. And to appreciate this feature, we will basically, first of all, alter the partition strategy of our flights table. Remember to use a Hive hue editor. And now you may recall that when we created this flights table, we specified the partition by year. Now we are adding also months. So in Iceberg, this partition change happens immediately because it's just an update in its metadata file, not in the underlying physical structure. And so we may see that basically it happened. So now the flights table has a different partition structure, not just by year but by months. And now, scrolling down the lab guide, you will see this statement, this insert statement is nothing but a way to add another batch of flights from the raw table. Of course, this statement will take a while, but what is important is that now this new batch of data will be partitioned into the flights according to the new strategy, while instead the previously loaded records still will be following the previous partition strategy. The job completed. Now let's go back to our lab guide and from the Impala U, let's run this statement, which is basically looking for flights of 2006 grouped by year and month. And there's no need to run this query because you lets you take a look over the explain plan without the need to run the query. And here we see an interesting information, which is that for data up to 2006, we need to scan our month into a year-wide file, which is why it shows here a scan over a 130 megabyte file. And we can see the difference if we by chance change the query to 2007 and take a look again at the explain plan. And now we can see that still we access a single file, but the size of this file is order of magnitude lower. So we are, because the second batch of the data of 2007 was loaded with the second partition scheme, where we partition by year and months. So the cardinality of the physical files implementing this partition is basically the cardinality of the months. So each file is much smaller, and so we are basically with that partition evolution, we are improving actually the performance of the table, adapting to new needs in a much more dynamic fashion. Okay, now it's time to take a look over another very useful feature of Iceberg, which comes out of the box, which is basically the ability to take snapshots, so consistent snapshots of the data of the table every time the table get updated. And so to test this feature, we need to basically come back to our Hive U editor and insert another batch of data, in this case the flights of 2008, into our flights Iceberg. Again, we're talking about some around 8 million of rows. It will take a while, since for this lab we are working with low throughput virtual warehouse engines. So be patient a while. Okay, now it has completed. It took a couple of minutes. Then next step is to use this new statement, describe history. So the Impala SQL glossary has been extended with new verbs to handle Iceberg features like snapshot creation, and describe history is one of that new capabilities. So, and here we see how Iceberg deals with snapshots. Out of the box, he has created over the lifetime of flights table some intermediate consistent view of the data across all the inserts that we executed in the previous steps on this table. You may remember first of all we created the table, and then we updated the table with the 2006 series, and then with 2007, and then with 2008. So what we will do now is to use another nice feature of Impala SQL, which is this statement, this predicate basically for system time as of. So filtering previous state we want by either choosing the timestamp or the snapshot ID. So coming back to our described history, we can see that if we select this snapshot ID, we should see content up to 2006 when the table was created. While instead, if we choose a more recent snapshot ID, or maybe better a timestamp, just for the sake of doing something different, we may see that the status of the table is different, is the most up-to-date, which is basically what is seen by standard users omitting this special predicate. So the last known state of the table is exactly the 2008. Now, such ability to take consistent snapshots out of the box opens new functional use cases such as auditing. So for instance, exposing BI users a consistent look into previous state of the business domain they are analyzing, but also bring into data lake some DBA capabilities such as, for instance, rolling back a data lake table that could have been messed up to the last working consistent state, for instance, which is exactly the topic into the next section of our lab guide, where you can find an example statement that can be used to roll back a table to a specific point in time with a simple alter table. Okay, now it's time to take a look over materialized view on Iceberg table in CDP, CDW in this case. So basically we are starting with we will start with this statement that we are going to bring into our Hive editor. We are going to disable Hive query cache, which by the way is a nice feature available on CDW implementation of Hive engine. That it's a very useful query accelerator feature, which is working out of the box in CDW. And then we are going to drop the previously created airlines dimension table. We are going to recreate it with as an iceberg format and populate then with airlines data coming from the row layer. And then we are going to issue this join, this select join between airlines and flights, just to take a look over the execution plan of this query. Okay. Now it's starting the join, and that's our result. So the result is the aggregation of cancelled flight grouped by airline code and months of the year, but we are most likely interested in take a look over the execution plan of the statement. So here in U we have a nice visual representation. So here we can see that we of course needed to scan basically the files into the object storage, and we are talking about 93 millions of records in the flights files, physical files. So quite a bunch of data, and to improve the performance of such kind of analytical queries, we can use materialized view. And if you come back to the lab guide, you can find a way, an example, to create a materialized view out of the same analytical query that we ran before. So let's run it. And now let's see whether this view has been created. Yeah, and it's been created. We can see it also in our visual browser on the left hand side of Hue. And now, since the materialized view is ready, we can rerun the previous example and see whether the execution plan has been changed. Here is the result. And as expected, we are now hitting the materialized view. And so in this case, by hitting this view, the performance of this query has been greatly improved. Okay, With that, we arrive to step number 6, which deals with data security and governance. In this section of our lab, we will see how Iceberg tables has been integrated into the so-called SDX framework. SDX stands for Shared Data Experience. In a nutshell, SDX is an umbrella definition of many market-leading open technologies like Apache Atlas and Ranger and some other, which offer a unified experience on data classification, tagging, lineage, and also, of course, authorization across all the kind of data that is managed by the CDP, so both structured, semi-structured, unstructured, at rest, in motion, and across all the engines that manage this kind of data. So let's see it in action. Let's come back to our console UI. Let's click on the main menu and look for the data catalog. Data catalog is a control plane service, which is the first entry point into data exploration of the different data lakes that has been provisioned and managed by the control plane. So in this case, we will select our own environment, which our lab is running on. We can filter the search, the exploration to Hive table and also to specific users, owners of these assets. And here we see all the data assets, in this case Hive tables, that we worked on along our lab. For instance, the flights table, our fact table, can be explored in terms of metadata properties, technical properties. We can add comments, description. We can add tagging out of an existing library of tags. We can explore the lineage, so the life cycle of this table from its state as AWS S3 directory down to its evolution into a Hive table and across all the other curation steps up to the materialized view that we configured in the previous step of this lab. And we can, of course, include into the lineage the so-called processing nodes. So the process services that were responsible of such transition of state from, for example, raw table into Iceberg table into materialized view. So the lineage is a very powerful tool to keep governance over assets that are managed by different teams inside a data lake, which potentially can host hundreds of thousands of assets. Now let's switch to policy section of data catalog, in particular to list all the authorization policies that has been defined for our flights table. And let's jump into our Ranger engine. And let's look, of course, from Ranger we can define access policies, masking policies, and also row level filter policies. So let's now jump back to our lab guide. Scrolling down. And the aim of our next exercise is to implement a simple row level filter policy, which in a nutshell is nothing but defining a rule to prevent users from seeing specific set of rows inside the table. So in our case, we will create a new row level filter policy. We'll name it out of our name, in my case GF row level filter. Table. Then we select our user, and then we say this user can select only rows whose unique career value equals UA. And so we confirm this policy. Policy successfully created. And then with that we can come back to our U editor. And try to see the effect of our newly created policy. Okay, and now you can see the results. So we didn't filter explicitly with the where condition, but because of the Ranger policy enforcement, we only were allowed to see and to make queries on the set of rows whose unique career value is UA, right as defined in our row level filter policy. Okay. Now we arrived to step number 7. Now it's time to present the data. We ingested, we curated, we prepared an analytic layer, and now it's time to present the data to the data analyst. And to do that, we will use data visualization, which is another service available inside the CDP Cloudera Data Platform, which is a quite powerful platform to design and deploy visual dashboard, not just for data exploration, but also for business intelligence. So we will basically implement a logistics dashboard to support data analysts of our fictitious company to analyze relationship between flight delays and issues with specific parts of flight's engines, for instance. And to deliver those dashboards, we will create a semantic layer over our Iceberg tables. So let's jump back into our CDP console. Let's leave the data catalog. Let's come back to data warehouse. Data visualization has been integrated into two services in CDP. One is data warehouse and the other one is machine learning service. We will use the data warehouse one. Let's click on data visualization and let's open the data visualization console assigned to our lab. Here is a landing page with a summary of all assets included into the repository of this data visualization instance. Let's go back straight to the data section. In the data section, we have a chance to create a new connection to the data lake. Well, honestly, not just to the data lake, but to a number of other databases. Let's stick, in our case, to our Impala engine. So we will establish a connection to our Impala engine. Let's give this connection a name. My host, my username, airlines Impala, for instance. Let's choose one of the virtual warehouse engines that has been created in CDW. Let's test the connection. It works, and connect. With this connection, we have a chance to explore in a similar way that we can do with Hue, to explore the content of the database catalog which that CDW Impala has been created upon, and to see also the content of our databases, flights table and all the other dimension table. And out of this connection we can create a data set. So a data visualization data set can be imagined as a semantic layer, so a logic abstraction of underlying tables without, of course, moving any data. So this is just a logical mapping in a way, in an aggregated way that enables the business intelligence navigation inside the dashboard. So let's give this dataset a title like I don't know, host GF logistic dataset, for instance. Let's start from a single table. This table is in our airlines, and let's start with the fact table flights. Let's take a look at this dataset. Here are some configuration options. Of course, there is a result cache that can be leveraged from the database or from Impala as well. So there are other kind of configurations. Let's go to fields. The tool automatically creates some measures and dimension out of the data that it can access. Right now there is just flights table, so of course we will change it as we improve the definition of this data set. So let's modify the data model. We started with flights as an initial configuration, but we want to extend this data set with dimension tables. For instance, planes, so to give a way to filter data based on planes. You can see that the tool has detected internal and external keys across the two tables, so flights and planes. We can edit this join by removing the ear, which we are not going to use it. We want also, let's reload the data and see how flights is starting to be enriched with actual data of each flight, actual data of planes associated with that flight. So just to, let's add another dimension table. Let's add airlines. So to be able to join unique carrier with code. Okay. And now let's add airports. Joining origin code of flights table with IATA code. And also by joining destination code from flights into IATA code. So let's take a look at our final data set. Flights, related planes, related airlines, origin airport, and destination airport. So we have created a nice semantic layer. Now it's time to improve some measures and dimension according to our needs. Now coming back to the field section, we need to change something in this definition, and we can review the instruction in our guide. So we need to basically change some metrics from measure into dimension. And so let's edit fields and follow the instructions. On the flight table, we need to change months, day of months, day of week from measure into dimension by clicking on that square. Depth time, departure time, arrival time, departure, arrival, flight number and year, and also from planes table and airports. All these series need to be treated as dimension. You can save. We will see that dimension has, the list of dimension has been increased. As expected, we also have to click on change the title case. Okay, and now let's change the title case and make a little change on this departure delay, which we want to be shown default as an average, not as a sum. And finally, we want an additional dimension that could represent the route of our flights. So let's clone origin as a starting point. Let's call it route, and let's specify the expression, the string expression, concat in this case, that we want this dimension to be implemented with. So we want to concat destination with origin. Let's validate the expression and then apply. And we will find here another synthetic dimension. Let's save. And with that, we can move on to the next step, which is creating the actual visual dashboard. Now, under this final section of our lab, we will create visual dashboard on top of the dataset that we just completed. And in particular, we will define a visual dashboard, a visual plot for the top 25 routes with highest average departure delay. And to do that, we will come back to our data visualization service. We will switch on the datasets that we just completed and click to this new dashboard. And we will land on this canvas where we will find the first default representation, tabular representation of our underlying dataset. And on the right hand side, we will find dimension and measure that we have seen before while creating the dataset as well. So we want some stacked bars representation, and of course to do that we need to select which is the x-axis, basically which dimension we want to aggregate by, which is our route, and the y-axis will represent the measure, the aggregated measure, which in our case is departure delay, which is average, because as you may remember, when configuring the dataset, we set the default aggregation function to be average. We can see intermediate results of this configuration. Now we need to put this stuff in order. So it will be top 25 top key, so it will order by average delay, descending, and limiting the results to the top 25 hit. We can now save this dashboard and look at the final results. And with that, the lab is completed. Thank you for your attention and congratulations.